Okay, so let's say you've done all your modelling, you've got your energy pie charts and your motion maps and your free body diagrams and all that. Having done all this, you can now apply some consistency checks to make sure that different parts of your models work together correctly. And I'm going to talk about 3 consistency checks. These are a good way to make sure that your model is sensible. Bear in mind that the vast majority of marks lost by students in exam conditions in this course are not due to stuffing up the maths, they're due to coming up with a silly model in the first place. So it's really important to check these things. Once again, it doesn't take long, it's a very easy thing to do, and it can help make sure that what you've come up with actually makes sense. So now, first of all, we're going to look at how you cross-check your free body diagram, which, if you remember, is a diagram of your object showing the forces acting on it, with your motion map, which is a plot of how something's moving. So let's see how this works. Let's imagine you have a ball or some object, and it starts off going upwards like that quite fast, and then a bit later is going downwards quite slowly. Okay, so that's our motion map. How about our free body diagram? So the free body diagram, let's assume that the forces are constant over this whole arc, and let's assume that there's going to be a weight and a drag force. Now let's just assume that's what you came up with. You've done your models and you've got your free body diagram here and your motion map over there. Let's check these for consistency. The way you check these is using F equals ma, which is a vector equation, so the vector force equals mass times the vector acceleration. What this means is the net force from your free body diagram should predict the change in velocity in your motion map. So what you do is you look at your free body diagram and you do a vector sum of the forces. So it's like combining them. The vector sum is down here, or alternatively you move one to the end of the other. So that's telling us that the net force, and hence the net acceleration, is in this direction. Now how does that compare to our motion map? Well, our final velocity should be the starting velocity plus the acceleration times the time. So our final one should be this plus something in the same direction as the force, something like this. So this is predicting that our final velocity should be something like that. If the time is shorter, it might be like this. If it's longer, it might be like that. But in fact, it's not like any of those things. It's much shorter. So these are not consistent. Another way to think about it is to look at the difference between the starting and the finishing velocities. Now the way you do that, you do your starting velocity, your finishing velocity, and you ask, what do you need to add to the starting velocity to get the finishing velocity? That's what a difference is. And to take this to that, you have to go like that. So what that's telling you is that this motion map tells you that the net force should be in this direction, whereas your free body diagram is telling you it's in that direction. They're both downwards, but one slanting left and one slanting right. They are different, therefore there is an inconsistency between these two, therefore at least one of them must be wrong. In this case, probably the drag force should be pointing in that direction, in which case the vector sum of the forces would be that direction, which can line up with this, so that would make more sense. But it could be there's something wrong with your motion map. What this just tells you is it raises a red flag and says, check, something is wrong.